We have seen the differentiation calculus. Now let's see the other side of the coin, the integration calculus. In fact, in the second section, we have already seen how, from a function, to get its gradient. That is the slope of maximum ascent in that point. Now, from the gradient, we want to go back to the function. We have to compute, in order to do so, the antiderivative of that function. And the antiderivative will be denoted using this capital F. And the antiderivative f will be such that if we take its derivative, we go back to its function f. So, but given a function f, there exists an infinite number of antiderivatives, and we will see in a minute why. So we have to find a way to express those collection of infinite number of derivatives. In order to do so, we define the indefinite integral that is characterized using this notation. The indefinite integral is the collection of every f such that the f is an antiderivative for f. Here it's already expressed why we are talking about an infinite number. That's the plus c. To discover why there are infinity number of antiderivatives given a function, let's take a look to the f of x equal to 2x. We compute the antiderivative, and we get, I told to you, that it is the squared of x times c. How can we check that this result is correct? Well, through the definition of indefinite integral, and in particular of antiderivatives, we are just to take the derivative and check if it is equal to the original function. So the derivative of this one should be equal of this, and that's true. That's exactly the example we've seen in the second section, introducing the differentiation. In fact, the derivative of a constant is equal to 0. The constant doesn't change respect to the variable, so the change is equal to 0, the variation is equal to 0 for all c as a real number. That's why we have this plus c down here, and that's why we get an infinite number of antiderivatives. The core is always the same, but we have a plus c, plus constant. Since the indefinite integral is a set of antiderivatives, it follows that the transformation is linear, because the differentiation is linear itself, and thus we can find some integration rules. On the left side you can see some of them. But note that, for example, we don't have particular integration rules for the quotient, the product, the composition. That's not obvious as in the differentiation part. In fact, indefinite integration involves a little bit more of thinking. It's not just an automatic computation. But historically, another type of so-called integral has been defined, the definite integral. So the set of antiderivatives was the indefinite integral. Here we are talking about the definite integral. And the definite integral is a method to compute the signed area defined under the function, as we have seen here. The signed area, again, remembers the signed volume about the determinant. But the key core is that the definite integral's goal is to compute the area. But the definite integral can be characterized using several, and I'd say slightly different, formal definitions. For example, we have the Riemann integral, the Riemann-Stieltjes integral, the Lebesgue integral, and a lot more other types of integrals. I say that the definite integral is that depends on the formal definition, because, for example, we will see that some in the next course we will see that some functions are Lebesgue we can apply to them the Lebesgue integral, but not the Riemann integral. So depending on the chosen definition, for some functions we might or might not be able to compute the definite integral. We will see that the Riemann integral involves the vertical histograms, while the Lebesgue integral will involve in some sort the computation of an area using horizontal. In this course we will talk about the Riemann integral. In the next one we will see the Lebesgue integral, talking about statistics. So let's focus on the Riemann integral, and let's take a closed interval on the real line. And we define the interval decomposition sigma as an ordered set of n plus 1 points, such that these are the points x0, x1, xn minus 1, xn in this form, while x0 is equal to the left extreme and xn is equal to the right boundary b. So using this sigma, this interval decomposition, we can partition the integral such that we get these collections of limited intervals. The interval decomposition also is uniquely induces a partition. If we get a one interval decomposition, we also get only one partition of the limited interval AB. But the same interval admits, of course, so the same interval AB admits an infinite number of partitions. We just have to choose different interval decompositions. So given this bounded interval and an interval partition, let's take care of a function f that goes from AB to R, abundant functions. And we define the infimum of f in one of the elements of the partition and the supremum of f in the same interval. This ik is one of the elements of the partition. So we are defining an infimum and supremum for each element of the partition. And what are? Well, this infimum is the infimum of f of x with respect to considering the x staying in this element of the partition, this interval of the partition. The same for the supremum. Now, from the infimum, we define the lower Riemann sum of f with respect to sigma, to our partition, and the supremum, from the supremum of f with respect to that interval, we define the upper Riemann sum. What we do here? Well, we simply approximate the value of f in ik as mk, and we multiply by the length of the interval, which is xk minus xk minus 1. So here we are writing the lower Riemann sum as the sum of the values of an histogram in which the values of each columns are the infimum. And this is the lower Riemann sum. In the upper we use the supremum. That's it. Here's the geometric interpretation. Here we have our function and we want to compute the area between A and B. The lower sum, the lower Riemann sum here, we take the infimum and we multiply. So, what's the area of the rectangle? Is the base, the length of the element of the partition, times the height. So we get our bin. And we do this for each of the elements of the partition. We get an approximation of the area, but using the lower histograms. We do the same using the upper, the supremum, getting the upper Riemann sum. Now remember that the sum, let's take a look at this, the sum of the length of the single partitions is of course equal to the total length b minus a, of course, because if we sum this plus this plus this and so on, the base of all these rectangles, we get b minus a, whatever is the number of the bins of the histogram. Also, we get that the infimum here is less equal than the minimum of mk. And then the supremum of f of x is greater or equal to the maximum of our supremum in the bins, in each bins. We can then write this up, because in here we have, let's get back, we have the height of this bin times the length, and we multiply by the number of bins. We can recreate this, taking care of the fact that the sum of this is exactly equal to b minus a, and this relations. So the minimum times b minus a is less equal than the lower Riemann sum, that is less equal to the upper Riemann sum, that is less or equal to the maximum times the length of the interval. Another step ahead is to compute the sup of this lower Riemann integral and to take the infimum of the upper Riemann sum. Each of these computations leads us to the lower Riemann integral and the upper Riemann integral. And this is the relationship. Of course, since we take the supremum of this term, we have that L is less equal than the lower integral. And again, since we take the infimum of u, we get that the upper integral is less equal than u itself. But note that in here, L and u depend on the partition we choose. But the two integrals here, since we are taking the supremum and the infimum, do not depend on the partition. So the two integrals, I say it again, do not depend on the chosen partition. And wrapping up together, given the function that goes from AB to R as a bounded function, if the lower integral is equal to the upper integral, then we write the definite integral in one of these two following ways, and we say that the function is Riemann integrable. Geometric interpretation of this may be complex, but we will see in a minute. We have here on the top the upper Riemann sum, and on the bottom the lower Riemann sum. As you can see, here we have a small number of beams, but we start to increase them. As we can see, the approximation gets closer and closer to the real area that underlies the function. And this should not depend on the partition we choose. So implicitly, when we do this definition using the lower integral and the upper integral, we are doing a sort of limit. Implicitly, we are taking a limit. And we say that we can compute using the Riemann integral, we can compute the signed area under the function only when the upper integral is equal to the lower integral. And we could have seen that if f is continuous, then it is also Riemann integrable. As I introduced in the first section, the differential and the integral calculus are linked together thanks to the fundamental theorem of integral calculus. And in particular, the fundamental theorem of integral calculus links here in this context, provides a link here between the indefinite and definite integrals. The fundamental theorem of the integral calculus can be divided in two sub-theorems. So let's see the first one. And we say that we have a function that goes from AB to R that is continuous here. And we have a capital F function such that this is the integral between a and x, where x is a variable, can change. Then, since f is continuous, we can see that capital F is continuous on AB, differentiable on AB, and thus that the derivative of capital F is equal to F, which means that this one is the formulation of an antiderivative. And this is equal, this fx is an antiderivative for all x in AB. So in here we are able to get the indefinite integral through the definite integral. In the second fundamental theorem of calculus, instead, we have f that is Riemann integrable. And we explicitly say that we have capital F an antiderivative. In here, then, we can write the definite integral as the difference between the antiderivative computed on B minus the antiderivative computed on A. So, in here, we say that the definite integral can be built from indefinite integral. And this can be seen in this animation. We have our function that has an area S. And here you can see the antiderivative. We want to compute, for example, this area. So we get this one and that one as small and as upperless. So the area of S upper S minus S is exactly equal of F of A of B minus F of A. One of the main tasks is to compute then the area. In order to do so, we have to refer to the definite integral. And we can use the fundamental theorem of integral calculus. For example, if f is continuous and or Riemann integrable. We compute, in order to do so, we compute the indefinite integral up capital F for a generic point. Then we evaluate f of x for the two extremes of the region for which we want to compute the area. And then we compute the difference between the two f of x, taking care, of course, of the order of the extremes. So let's do this in this example. And we have this function, which is an inverse parabola. We want to compute the area of underlying this parabola between x equals 0 and x equals to 4. This one, this definite. This is our definite integral. How we can do this? Well, step 1, is f continuous or Riemann integrable? Yes, it's continuous. And with this, Riemann integrable. Step 2, we have to compute the indefinite integral. In order to do so, we just apply, I don't want to deep down into the integration rules. We get these results. Please note that we have the plus c here. We have a family, a collection of antiderivatives. Step 3 and 4, we compute f, the antiderivative, the indefinite integral with respect to 4 and 0, and we take the difference between the two. Also, the This difference can also be written in the result of the indefinite integral. Sometimes we forget about plus c, since as we will see, this plus c is insignificant, of course, to the computation of the area. And then we get this vertical line to describe the limit. In here we get, in fact, that the c is insignificant because it simplifies between the first and the second indefinite integral. Here we get that the area is approximated 10.7. So this was the course number 4. What we've covered here? Well, we introduced the concept of limit, and this concept allows us to analyze the behavior of a function when approaching a point, not just in the point itself, but the behavior of the function around that point. And thanks to this notation, we can also identify functions that are particularly regular, the continuous functions. Then we have seen how we can use the limit to compute the rate of change in that point of a function, how the change instantly varies around that point, which introduced us to the differentiation. We've seen that the direction of the steepest ascent is the same direction of the gradient. Then we have seen that there are two types of integrals, the indefinite integral and the definite integral. The indefinite integral comprises all the antiderivatives for a given function and a given point. The definite integral, instead, allows us to compute the signed area under the function. The two concepts, the indefinite and definite integral, are linked together through the fundamental theorem of integral calculus. Now, we are able to compute how function changes, and everything interesting changes. With these tools, now we are even able to appreciate that. See you in the next course.